Thanks, Ryan. And if anyone else is interested, we definitely want to, encourage any other job opportunities to, that people have to bring them up and promote them here. So just reach out and let us know. All right. So for tonight, our speaker is Frank Maldari. Thank you for coming. Frank is the technical director for IM Photonics, a company he founded in 2003, which specializes in custom optical thin film coatings. Prior to starting IM Photonics, Frank was president and product development manager at OPCO Laboratory, where he developed e-beam and ion plasma coatings. Frank's background includes a BSEE from Worcester Polytechnic Institute, and MSEE from Northeastern University, where he concentrated in electro-optical design. His experience also includes systems engineering and management at iTech Corp and Inspex Inc. And without further ado, thank you, Frank.
Thank you. Thank you for inviting me here. I see a lot of people that I know, and I want to just point out that if anybody has any questions or would like to add anything to what I'm talking about, please feel free. I have been doing these thin film coatings for quite some time, but I don't know everything. And when I started doing this presentation, I realized how broad a field this actually is.
Super. Sorry, you can keep going.
So what I'm going to present is what my experience has been and what my knowledge base has been on thin films. But I do realize that there is a lot of other applications. So let me get started here. I think I can.
Might need to be aimed at the
this here high technology.
Not sure that's working.
Oh, okay. All right. Let's see here.
Let me see real quick. Oh, sorry about that.
I'm definitely old school.
Oh, there we go.
Okay. All right, great. All right, so so I wasn't sure where everybody was coming from in terms of optical thin film. So this is kind of the agenda that I'd like to go through on the slides. History, applications, how we as designers select materials, how optical coatings are specified, and bring you through design, production, testing, and other uses of the thin films. Okay, good. Okay, so I was talking to a gentleman who said that he has some information on the history of thin films. So let me briefly go through what I know. And if anybody else wants to add anything, please let me know. Or if there's a error, let me know. So from what I understand, we're talking about, optics in general have been around for years, right? From the ancients. And actually optics in general, it also goes back to the ancients, Egyptians and Greeks and Persians. But interference coatings, I think, are relatively new, right? When we say relatively new, to this Isaac Newton era, where he first observed interference fringes on two flat plates. And then researching this a little further, Fraunhofer had other observations about reflecting films on glass, where he noticed that something was depositing on glass that was actually making the glass less reflective. Also observing different colors on soap bubbles. Then there were further investigation by Lord Rayleigh and Dennis Taylor on optics and reduction of reflection on the coatings. Then from the early 1900s, with the development of vacuum and pumping systems, the technology for producing coatings started to take off. Then, jumping ahead even further in the 80s with computers and the semiconductor industry providing a lot of the equipment that thin film coaters needed, we saw another big development. And then in the 90s, where I started getting more involved in coatings, was the introduction to ion beam technology. And so nowadays we have quite a lot of equipment at our disposal to make very sophisticated thin film coatings. There was a gentleman that knew something about the first actually thin film.
I can say a few words. Basically, in 1930s, this was 1934, there was a scientist originally from Ukraine, Alexander Smakula, who went to study in Germany and in Göttingen, got his PhD there and stayed there. He worked for Zeiss. And in 1934, he basically did the first magnesium fluoride coating, or air coating. And this was developed as anti-reflection coatings in the layer. This was like really the first thin film. It was quickly classified because it was used for gun sights.
You're right.
Yes. But it became kind of known later. He worked in Germany through World War II. After World War II, he was brought to the U.S. As part of Operation Paperclip, which brought von Braun and other scientists. So he was brought here. And then eventually he came to MIT as a professor. And he ran a crystal physics lab. They were going crystals, various studies studying crystals. So when I came to MIT, I kind of worked in his lab. So he was already retired, and like old gentleman coming in. He said, "Oh, I did the first AR coding, and what did I know? It just a small guy."
Yeah, but that was significant, you know that.
Alexander Smakula.
Yeah.
He passed away like in the 90s, late 80s.
Well, I think he would be very proud to see where the industry has kind of gone today. You know, all starting with that one coating. But I just find being in the industry so long, doing it since I was in college, I just find it fascinating. All the developments that occurred and all the people that have been in it.
I think there may be some AR coatings related to Langmuir Blodgett or Catherine Blodgett here pretty early. Kind of lost.
Yeah.
Thin molecular.
Right. I think the area of thin film coatings, my experience has been mostly with the optics industry and supplying it to equipment manufacturers. But when we're trying to design a new coating and I have to research a new type of film, I am amazed at where I can actually find the information, all these other fields that you never even knew existed. Okay, so pretty common slide here. The different applications that we work with are mostly in the high-tech industry, where we're applying metal coatings of aluminum, silver, and gold for a spectroscopic application. And our interference coatings are generally used for laser systems, where we're designing specialized anti-reflection, high reflector, beam splitter, dichroic filter, and polarizer coatings. And these pictures just show some of the applications of those for thermal imaging. Let's see if I get this. Oh, that's not working.
Another way, if you want to try this, you can use
I think I have one.
So you can also just use this directly and then people can.
Okay. All right, thanks. Okay, so let me just go to the next slide. So here is just a little bit more technical information on these coatings. For just basic aluminum mirror coatings, that coating has the broadest reflectance range. Does have some drawbacks. One, it's soft and it oxidizes easily unless you put a protective overcoat on it. But aluminum has good reflectivity, especially if you're working in the deep UV, as long as it's contained and kept away from moisture, usually in a system that's purged with nitrogen. Again, we can protect it with a mag fluoride overcoat. You will lose reflection below 190 because of the absorption of the mag fluoride, but it still retains most of its reflectance over a very broad band in the UV. That's really the only good metal to use if you're looking for cheap UV reflectance mirrors. But aluminum also has benefits in the visible and also in the near IR, as long as we can protect it to make it hard with usually a quartz or an SiO2 overcoat. And then with other dielectric films of high index and low index, we can actually enhance the reflectance practically to 95, 96%. And just rounding out the other metal coatings, would be silver and gold for reflective purposes. And bare silver has very good reflectance. You're usually getting above 97%, 98.5% in the near infrared, and it has good reflective qualities in the visible, way beyond aluminum. The downside, again, is that silver is a soft metal and it needs to be protected. And we usually are, when I say we, I mean people in the industry will put a quartz overcoat or a sapphire overcoat onto the silver. You do lose some reflectance. You can see on the top curve, it's expanded out scale, so it will drop 96.5, 97%. But that, depending on the thickness of the overcoat, you can tune where you want the peak reflectance to be. And gold has the best reflectance in the infrared, but it's inert. Nothing wants to stick to it, so you usually have to use it as a bare gold coating. You can protect it to a degree where you can do some minor cleaning, rinsing on it, but it's still a soft metal. And to get that 98% with physical vapor deposition, it's just going to be a very difficult coating to clean. But it's going to give you very good reflectance in the infrared.
Question?
Yes.
Not an expert on this, but can you vary the substrate that you're making a reflector out of so that some of these metals stick much better?
Well, we do. So gold is not deposited just as gold. There's a binder layer that's always put underneath. Usually it's chromium. And that binder layer will help that gold stick to any metals or glass. So usually chromium is what we use for a binder layer on that. Or you can actually use an alloy too. Nichrome will also work as a binder. Any other questions? Okay. This is what the industry uses what we call interference coatings. So multi-layer interference coatings relies on these high and low index films of specific thicknesses and indexes to interact with each other, to interfere with each other, either constructively or destructively, so that you either enhance or retard the reflection of light. And this is just a quick list of some of the more common multi-layer interference coatings that are produced in the industry, from single-layer mag fluoride, which this gentleman had explained was the first, to anti-reflection coatings that would involve multi-layers, so that you would get lower reflectance, and that's what's, see if this was working again. So that's where the red dot is. Like this would be, let me see here. That there is uncoated glass. Single layer mag fluoride would be this yellow, which gives you 1.5% at 550. Again, based on the thickness, you can tailor this for any wavelength. And mag fluoride has a very broad wavelength band, so you can actually use it for AR coatings in the UV and the infrared. And then finally, if you do like a 3-layer design, you can get even lower reflectance and a very broad bandwidth on that. Going down, if you want to design a 25 layer coating, you can get better than 99.5% reflectance. Each layer is designed for a specific wavelength based on the thickness. And I'll explain that more later. Just other coatings are dichroic filter coatings, and also coatings that we can put on the hypotenuse of right-angled beams, right-angled prisms, and form beam splitters. And that, in this case here, this is a 70-30 split beam splitter, all done with dielectric interference coatings. Okay, so these are the different materials. When I talk about dielectric films, these are films that have different indexes of refraction. And we break up the materials into the spectral ranges that we want to use them in. And this is not a complete list, but these are the most common materials that we use for the wavelength bands that we're usually supplying customers with. So for the UV, low index, 1.386, 1.45,
magfluorine than SiO2. Aluminum oxide is more of a middle index of 1.62, and hafnium dioxide and zirconium oxide are roughly 1.95 to 2.0 index of refraction. In the visible, you still have the same material, but we added titanium dioxide, tantalum, and yttrium oxide for materials. They absorb in the UV, so they're not classified as UV film materials. And then in the infrared, out to about 2.5 microns, the same materials apply. We have to be careful when we start working in the near infrared and far infrared because they're absorption bands. If you look at the radiation spectrum, and especially with oxides, you'll see around 2.5, 3.5 microns, and I believe around 7.5 microns. And so these films will be highly absorbent in those spectral regions. If you're outside of those spectral regions, you get away with the use of some of these oxides. But to be safe, we tend to stay away from them. And most people in the industry will be using some form of a fluoride. And there are different fluoride compounds that manufacturers make. I think Materion produces IRX, which I think is a cerium fluoride-based material for the infrared. Zinc sulfide, you can evaporate germanium or silicon for your high index materials. And this picture here shows what some of those materials look like that are put into the electron beam gun. This is titanium, which has characteristically has a nice melt on it, pretty stable. This is hafnium dioxide and zirconium oxide. Those materials are more difficult to evaporate and form a film because they sublime. They go from the solid to the gas state with a very small liquid state. They tend to be very volatile. Silicon dioxide here, granular, silver, and last mag fluoride. These would go right into an electron beam gun. Just quickly, this happens to be just one example. This picture here is courtesy of Materion. They supply a lot of the film material that the industry uses. In this case, it's aluminum oxide. So as designers, we rely on this data to guide us on how to evaporate something like aluminum oxide. And we look for the wavelength range and evaporation characteristics, substrate temperatures that they recommend that we deposit it on, and what the partial pressures of oxygen we have to use. The reason why we have to do that is that all of the oxides that the industry uses, when you evaporate it with an E-beam gun, the molecule disassociates. If you're doing tantalum pentoxide, the tantalum and oxygen molecules will separate and they will recondense on the film as a film on the substrate, but they don't always recondense it the way that it started the evaporation. So you have to partial fill the chamber, the vacuum chamber, with oxygen. And with the right temperature of the substrate, you hope to form, this is where a lot of the art comes in, tantalum pentoxide, but not some other film like TAYOX. And that creates problems as far as what you're counting on when the final results of your film. And then a lot of companies spend a lot of time trying to come up with those exact values, and that's where the art of the coding comes from. Okay, here's a shameless plug for the OSA. Being in the industry for a long time, I've had to deal with all these mil specs, and they're all similar, but all a little different. Some have to do with front surface mirrors, some are single layer mag fluoride coatings. They're all very good, but a lot of them haven't been updated since the 80s. I started getting involved with ISO specs, and an ISO, I find that the 9211 to be a very good book for reference for coating. So if you're an optical engineer and you need to work on specifying optical coatings, from my experience, I would recommend the 9211. And you can get it from the Optical Society or Optica online. But that's a good way of if you're just new to it, to get that and flip through that. I did, and I know that with the ISO at all the major, well, I know at Photonics West, they're always meeting and going over the standards and constantly updating. Any questions? Okay, so this is right out of what they give us an example from the ISO book and how to specify coatings. Unfortunately, the slide is hard to read, but on the print, what we see as designers, we look for this symbol here, which is the lambda in a circle. Sometimes it appears in the drawing, but most often it's in the specification table, which defines the radius of the lens and the materials. And you'll just look for that symbol, and that's what it'll be there. In case of this drawing here, what they give us is that the lens is an SK11 with an index of 1.5638. The specification for the application is they want looking for reflection of less than 1% at a wavelength range of 460 to 640. Now, what we have to assume in this case here, from a designer's point of view, that the lens is operating in air, because that makes a difference on the design of the AR coating. So we assume that air is 1.0. And also that the angle of incidence is 0. As the angle changes, the reflections will change, and the design of the coating has to accommodate that. Very basic drawing of how interference coatings work is, again, you're dealing with the reflection of each surface of this AR coating. In this case here, we're taking a standard quarter, half quarter AR coating. And these formulas that we use in the industry are really taken from work that people have done in the past, that have experimented. We're building on the knowledge base that already exists in the industry. Books like from Baumeister or McLeod give all these recipes for people to start their designs for. So rather than reinvent the wheel, the industry just basically uses what's already been done and tries to tailor those designs for specific applications. So this is a standard quarter, half quarter AR coating. And the materials that we would select in this case here are aluminum oxide, tantalum, and mag fluoride. And these are the visible materials. So as the incident light reflects off of each surface, the top layer being the first layer is aluminum oxide, layer 1. Second one is tantalum. Third is mag fluoride. The reflection off of each of these layers produces a wave front that either interferes constructively or destructively. And we're designing these coatings so for an AR coating, you get destructive interference. For a high reflector, we want constructive interference. But we want to reduce it, so we're designing it with destructive interference. And that design will give us a model that looks like this curve here, where we're getting basically less than 0.5% average from 450 to 650. And the spec on the print was 1%, so we're well below that. Okay. We're getting a little more sophisticated here. Again, we take a basic formula for this application, which is a dichroic filter, where we're transmitting visible light and we're rejecting infrared light. And so in a case like this, we start with, again, building on the knowledge base that exists in the industry, a formula based on quarter waves. Something about quarter waves. So my understanding on when people were dealing initially with measuring and doing these coatings, we actually had a strip chart recorder, and we would actually see as we deposited the reflectance on whether it was a quarter wave or a half wave. Now that's all done with computers. We don't see that anymore. But when I first started in 1978, I worked for a company called Spectrum Systems in Waltham, and that's how they measured all their coatings with a strip chart recorder and either a laser or a white light source and a chopper wheel. And the technicians would just truncate the coating thickness or shut off the coating thickness as soon as they saw that needle reach the peak of that quarter wave. So in any event, it's a side note. We take the formula, and this is TF Calc. TF Calc came out in the 80s, and it's one of the, more popular thin film coating software. The nice thing about it is you can take the formula, plug it right into your formula equation, specify your material, what you want for high and low index, and have it generate the layers. In this case here, this is a 33-layer dichroic filter of alternating high and low index materials of SiO2 and tantalum. And each layer of tantalum is the same, except for, of course, we're doing a quarter wave here, an eighth wave, and then this is a 1/4 wave. And they're all the same. The problem with an initial design like this is that since they're all the same, you're going to get harmonics. And that's what you see in the passband here, all these harmonics. And that's usually a problem for instrument manufacturers. They want to see nice flat top passbands. So what we do is they have algorithms in the software that you can define and work with reducing the harmonics in the passband. So this is an optimized coding. We define what we want the optimization to be, how much variation in the transmission. And the software, I don't know what the algorithm that they use, but they'll do an optimization function, similar to what you would do for, I think, ray trace designs. Now, what the optimization will do is it'll no longer be exact quarter waves. It'll give you more of an asymmetric thickness. And that's something we have to deal with when we program the material in the coating chamber, which is where we're going now in production. Is there any questions anybody has so far on anything? Okay, so this is a typical physical vapor deposition system. It's a vacuum system. We use a cryo pump and a mechanical pump. And I was talking to a gentleman earlier where they still used in the college was a diffusion pump and some of the problems that creates. But the cryo pump gets down to a very low vacuum, 10 to the minus 6, 10 to the minus 7 torr, which you need when you're depositing films. Because if you're going to deposit tantalum pentoxide, you don't want to deposit tantalum pentoxide in nitrogen or carbon or anything else that's floating in the air. You want to have a good vacuum so you get good stoichiometric properties of the film. So good low vacuum is essential. Since we're doing physical vapor deposition, the amount of energy that the molecule has when it arrives at the substrate is going to be limited to the amount of energy it's carrying with it when it gets evaporated. And the further away it is, the less energy it's going to have. So we have to preheat the substrates to increase the energy level so that you can get good molecular bonding at the substrate level. So we preheat the substrates, depending on the type of substrate, up to 250 degrees centigrade. So it gets very hot. We can augment that with ion beam bombardment from an ion gun using argon ions. That adds more energy to the surface. And actually, as the film's growing, what the argon ions are doing is they are breaking down the columnar growth that you would get with the film growth. And it pretty much makes it more of a denser coating. You can get higher indexes. So we use ion beam technology to assist our deposition. Again, we use the E-beam, electron beam gun, for evaporating those materials I showed earlier. The reason is that those materials are evaporating. You need something like around 2000 degrees C to evaporate many of them. And the only way you can get that much energy is with an electron beam gun to do physical vapor. And again, the ion beam to actually assist in the deposition. And also, we plasma clean the surface of the substrates with the ion beam to remove any contaminants or monolayers to get good adhesion also. And this is what the system actually looks like. Remembering the chart earlier, you can see the planetary rotation here with, these are the substrates. These happen to be lenses that are 10-inch diameter fixtures. It's a double planetary rotation. Each fixture rotates and the whole planet revolves around the chamber. And that's because with physical vapor deposition, you don't have a uniform plume of material that's condensing. It's distributed radially. So it may be very high concentration of film coming from the E-beam gun, but as you get further away, you get less concentration. So the thickness would be thinner. In order to get the uniformity, we have to rotate the substrates in and out of the film plume, if you will, in order to even out the thickness distribution. We monitor the thickness of the coating as we're depositing with 2 crystal sensors. In this case here, there's one in the center and there's one here on the edge. And we average those 2. And the film that's condensing on the sensor is not exactly the same film thickness that's on the substrate, but we qualify the system by determining a tooling factor, the ratio, what condenses on the crystal to what is condensing on the substrates. And that's programmed into our deposition controller. So and that stays with that system as long as we don't change the geometry of the chamber. Again, we use substrates heater to bring the substrates up to temperature, and ion beam to assist in the film formation. For more cost critical, where batch size is important, we can scale that up to larger sizes. We can go longer coatings with dual E-beams, so we can evaporate more material for more layers, longer deposition coatings, and we can handle larger substrates. But it's the same technology, just scaled up to a larger system. Earlier, we talked about some of the metals that we do, aluminum, silver, and gold. Those are low temperature evaporation material. Some of those films don't like to be evaporated with an E-beam gun. The E-beam is water cooled. It draws a lot of heat away from the source. And when you have a low temperature material, you're drawing heat away faster than you can actually apply it to evaporate the material. If you apply too much, it's going to spit and spatter. So the industry uses filament evaporation. This is aluminum here, and this is actually SiO here. And this is to produce a protected aluminum mirror. So even though E-beam and ion beam guns are, fancy, this technology has been around probably since the 30s, probably, when they first started evaporating that fluoride. And I can't leave out sputtering, which is a whole different type of evaporation. Rather than relying on the energy of the molecule as it evaporates, leaving the gun, you're creating an electric field, a plasma, between the source and the substrate, which helps you to have better stoichiometric uniformity of the material. With physical vapor deposition, you have to be very careful on how you control the deposition, because if you don't do it right, you get films that are inhomogeneous. May start out at one index and end up at another index. With sputtering, it's much more reliable. What you start with, if you're doing a thick film, it ends up the exact same stoichiometric parameters. So I need to mention that also. And in addition to that, you get because the energy is a lot higher than regular physical vapor deposition, so you get denser film growth. You can do it at low temperature. And also the chamber does not have to be cleaned as often. You're restricted to just the area between the gun and the substrates where there's material, and the chamber will pump quicker and to lower base vacuums.
Do you use the same materials available?
Yes and no. You can produce the same films, but not use the same materials. Caitlin is our principal scientist who's been working on the sputtering, and she's been experimenting with different materials. And one of the things is that I talked about tantalum pentoxide, right? Where you buy from Materion, actually tantalum pentoxide. With sputtering, you can't evaporate, well, at least with pulse DC magnetron sputtering, you can't evaporate tantalum pentoxide because it will, what's the term?
It will insulate.
It will insulate. Yes, so you start with tantalum. And so you use argon gas on the sputtering for the tantalum, but you would introduce the oxygen through a oxygen distribution ring. Well, if that shows it there. No, this one doesn't have it. This is the, we've added it later. This is our tantalum target here. This is an argon distribution ring, but we have actually put in another oxygen ring near the substrate. So we're actually evaporating tantalum metal, and we're creating tantalum oxide right at the surface of the substrate.
Are the stresses on the substrate when the deposit films lower when you do the sputtering than the ion beam, or is it just the opposite? You know, the compressive and tensive stresses that you get the constant chips out of your coatings.
Yeah, so that's a good question. So when we do physical vapor deposition, we use SiO2, and whether it's tantalum pentoxide or titanium. So those are compensating stress films. One is compressive, the other is tensile. I'm assuming we haven't had that problem now because our coatings, you know, we'll go up to about 50 layers. So we don't see big issues with stress. We do work with one company, but it's not where they are concerned about stress, but but they are measuring that for us and they haven't reported back a problem. So they compensate. I mean, if you have a thin substrate and you put on a high stress coating, it's going to change the shape of that and it's going to change your wavefront.
But the question, sorry, maybe I misunderstood, but I thought the question is, do you get more or less stress with sputtering? With
sputtering? I don't think we've gotten that far, but you maybe.
From what I understand, sputtering produces denser films which are higher stress, low stress coatings.
Unfortunately, Dave, my experience, Caitlin's experience is more with sputtering. So I put that in because I can't leave it out. But my experience is more with physical vapor deposition. So, and that would make sense that, yeah, a coating that's more dense is going to have more stress.
Yeah, but this, sorry.
No, that's okay. You can, like I said, I don't know everything on.
Yeah, we're dealing with optical coatings on MEMS structures such as thin silicon membranes. So stress is very critical. So we actually not just try to get it low, but we try to control it with the controllable stress. And my understanding is that the E-beam kind of what we use is in the works well. We can control it, but the sputtering brings too much stress.
My question is all 50 years out of date. So.
Yeah, I mean, most of the time we're dealing with very thick substrates. In our case, you know, we're 1/4 inch, 10 millimeter thick substrates, and so we don't hear a lot about deformation of the substrate due to the stress of the film. I do know that, if you're working with laser mirrors that are 20th wave and you put a 25 layer high reflector coating on it, well, that 20th wave is probably going to be, 8th wave when you're done. So that will affect that. And if the substrate was very thin, yes, I'm sure it's going to affect that. Okay. All right, so it's getting late, so I'll just really quickly go through this. If anybody has any questions about substrate preparation, let me know. There's different ways of doing it, but the most important thing is that you want to make sure that the surface has no tension on it. And we do a water break test where we just make sure that if there's tension on the surface, which would cause issues with streaks in the film, after we deposit it, you can see it actually by running it underwater, and you see where the water is sticking to the substrate. After it's cleaned, it should just run right off. We also use ultrasonic cleaning. The industry uses that because if you're doing high volume, you don't want to have one technician spending all day cleaning parts. So you can use for critical parts, yes, you do, but for high volume work, ultrasonics is the way to go. Post-coating evaluation. So we want to make sure that the coating we design and that we deposited meets the customer's expectation. So we use spectrometers ranging from 190 nanometers to 22 microns. There are dispersive spectrometers, or the for the 190 to 3 microns, and FTIR for 2.5 to 22 microns. And in this graph here, one shows the actual measured one is blue, and in yellow is the actual theoretical design. This was our standard quarter wave, half-wave, quarter wave AR coating, standard in the industry. Everybody does this. It's a W coat, they call it, because it's shaped like a W. But we do this so often that statistical process controls allows us to have very good repeatability on this. Just some of the other tests that are also mentioned in the ISO 9211 is adhesion and abrasion. Typical tests for those for adhesion is just a standard tape pull test, where you would apply tape, Scotch tape, to the witness sample and pull it and then to inspect it to make sure no film has come off. Abrasion, there are two types, cheesecloth for moderate abrasion and the eraser test for a hard abrasion. Gold will not pass the eraser test, but hard dielectric coatings will. In addition to that, we do temperature and humidity, standard environmental testing. Okay. Surface quality, scratch dig, also in the 9211. Depending on the, 8050 is more commercial quality, 105 is laser quality. Depending on the application, you don't want to overspecify this, because try to do optics and coatings at 105 when you only need 8050 is going to cost a lot of money. Chamber has to be specially prepared. Film has to be properly outgassed. There's a lot of prep work to go into that. So you have to be careful of what your application is and how you specify that. In those, that surface quality is referenced to standards. In this case here, these are scratch dig standards. 80 being the scratch, 50 being the dig, and as you go down, the number gets smaller and smaller. And then this is just a picture of those actual standards. It gets very difficult to see without the use of a microscope and high intensity light. These are some of the other uses of thin films that are kind of related to the optics industry. So we also, in the industry, have been working a lot with hydrophobic coatings, and these are coatings that are more used for humid environments where you want the moisture to actually run off the coating. So in this case here, these hydrophobic coatings are measured by applying a drop to it and looking at the contact angle that drop makes with the surface. Coatings that are not hydrophobic, that drop will tend to spread out onto that surface. In addition, other coatings that are optically related are ITO, or conducting coatings, which are important in the optoelectronics industry, as well as semiconductor industry passivation coatings to prevent diffusion of contaminants to the wafer. Cost considerations. Let's see. Just briefly, for metal coatings, gold, I think today is at $2,000 an ounce. So unless you really need it, that's going to be an expensive coating. Whereas aluminum is 0.7 cents an ounce. Multi-layer interference coatings. The thing to be careful with that is, again, over-specifying. The cost is going to increase with the number of layers you do, because it's going to be in the chamber longer. It's going to require more control. Filter coatings tend to have the highest layer count due to the transitions between reflection and transmission. The more layers, the sharper the cutoffs that you're going to get, the narrower the bands you're going to get. Again, that's going to add to the cost. Again, also the wavelength you're working with, the deposition time, since interference coatings are a function of the thickness, and the thickness is a function of the wavelength, the further out you go into the infrared, the thicker the layers are going to be. The thicker the layers are, the longer the deposition time, the more expensive the coating. So these graphs just illustrate those relationships. So the important thing to remember is that when designing a coating, you want to work with the coating vendor to optimize the coating for the application, not to over specify that. Any questions? Okay, so in summary, optical thin film coatings, you would think that it's a narrow field, but it's actually quite a lot involved. We think that it plays an important part of the optics industry, but we feel that working with the designer and engineers will always produce the best results. We hope that this presentation fills in a lot of gaps you might have on thin film coatings. And I want to thank David and NES Optica for allowing us to present this talk. And just for a few credits, Materion, their data sheets have been very helpful to us, and also TF Calc for their thin film coatings. And I would also like to thank Caitlin Mason, Michael Moldari, and Michelle Moldari for helping me put together this presentation. Thank you. So, is there any questions? Yes.
Even showing the list of materials that you make coatings out of.
Yes.
You showed materials with one index listed next to it, and then you said, "Oh, and we use these over 190 to 700." But these are dispersive materials.
Oh yes. Okay.
How do you deal with the fact that you're
okay?
Don't have the same index.
Great. Okay. That index that I gave you was probably just at 550. But let me go back here. Okay. This is where the material vendor data sheets are very important. So if you look at this top graph here, it gives you the dispersion of that material. So what we do is with TF Calc, and I'm sure it's the same with FilmStar and McLeod software, you take a material, you define it, and you put in the dispersion values so that when you design the coating, that software knows, oh, I'm running between, say, 190 and 350. I'm going to be using 2.5 as my index of refraction for that material. So it has a lookup table that it'll refer to for the range that you're actually designing that coating for. So that's a good question.
Kind of follow-up question. You mentioned, particularly, you mentioned a lot of like transmission and reflection percentages, but there's no absorption. Is that just because of the thickness of the films?
There's always absorption.
Negligible?
Yeah, there's always absorption. We tend to ignore absorption because it reaches a limit or you can't measure it. There is ways of measuring absorption, but with oxides and these interference coatings, the material that we select are specifically for low absorption. Now, with physical vapor deposition, you are going to get some absorption no matter what you do with your partial pressures and trying to get the right stoichiometric properties. So in the industry, what we do is we have to post-bake the coatings for some of these oxides in order to basically re-energize the coating and re-oxidize it to lower the absorption. And so it also to relieve some of the stress that might be in the coating. So there's kind of like a post-annealing, but it's more of a reactive baking that we do on the film. So a lot of times with tantalum pentoxide especially, it has to be post-baked in order to reduce the absorption. There are some materials like hafnium dioxide, has much less absorption, doesn't need to be post-baked.
Do you load the machine with more than one coating material and somehow rotate it in, or do you?
Yes. So good question. Let's see if I get to that. The E-beam gun here, that's a in the lower right corner. That's a 6-pocket E-beam gun. Each material is it's a 40 cc crucible, and so we can put in up to we can put 6 crucibles of the same material, 3 of tantalum pentoxide, 3 of SiO2 if it's alternating materials. If it's like a 3-layer coating, we'll put in 1 crucible of aluminum oxide, 1 crucible of tantalum pentoxide, and 1 crucible of baric fluoride. And so we can alternate between those materials. With the larger chamber, we actually have two e-beam guns where we can put in 4 materials on the one on the left, and then an e-beam gun on the right. It's actually a big circular crucible where we just fill that with SiO2, one material, so that we can alternate between the two. And the benefit of a system like this is as soon as one layer is done, the other e-beam gun is ready to go. So there's very little lag time between each of the layers. Yes, Amy.
I used mag fluoride windows some years ago.
The window is mag
and
fluoride.
They were wonderful. They went into UV. They went outside. They didn't degrade under a vacuum. You know, the other, except for one problem, they were birefringent.
Yes.
So, how do you know, is it amorphous, microcrystalline? At what level do you control that in a way that allows you to dial in the index of refraction or orientation or
well, we don't.
whatever?
So when the film grows, it doesn't grow with physical vapor deposition and sputtering. I don't know. We don't have as much experience, but it doesn't grow amorphous. So it grows crystalline. So we don't see the birefringence that you would get in a mag fluoride crystal. So that we have not seen.
So the properties, so when you're trying to put the numbers for index of refraction and stuff like this, and you get the number for the material you're getting out, basically.
Yeah, I mean, there's no, we don't, I mean, try to think of some of the birefringent materials. I always see it in substrates where you have the two indexes that give you the birefringence, but manufacturers for the sub materials, they just give us the one index. And even that index dispersion is not going to, that's just the starting point. Each system is going to give you a different dispersion profile just based on how you're evaporating material. But no, we don't see ordinary and extraordinary indexes for the materials.
Imagine it's thickness dependent. And that's where a window or whatever that might be millimeters versus nanometers makes the difference between.
Right, you get the separation of the axes, the thicker the substrate, like Daniel says, is correct. Yeah, as a substrate, mag fluoride, calcium fluoride materials are difficult to put a coating on. They're very soft. They stain very easily. It's very difficult to clean them. We have done them, but on lenses, mag fluoride lenses, it's a tough material. It's a tough material to deal with.
Yeah.
Josh.
What's going on with the call out that I always see? No radioactive materials, no cooling.
Okay. That's thorium fluoride. Thorium, when I started in 1978, you could smell thorium fluoride throughout the building. You could smell diffusion pump oil. It was a great material. It stuck to everything. It had a great index. It was being used for everything, protecting silver mirrors. Everybody, and I think companies still use that. But to do military work where, you know, they're very sensitive, like on submarines or, you know, nuclear powered aircraft carriers, the Navy doesn't want to see any radioactive material. And also, you know, people were very lax in handling it. They weren't, you know, very careful. And, you know, you can get a lot of, you know, low radiation exposure constantly from that material. So it was best for the industry to find alternatives to that. And I hate to keep on plugging Materion, but they were like one of the first companies to come out with thorium fluoride alternatives for thin film coatings. But yeah, that used to be, everybody used thorium fluoride.
I've always been fascinated with how nice the coating layers are controlled in the process. So that you showed the crystal sensors. How do you leave that exactly in a half a quarter?
Yeah, good question. So when I started in the industry, they used optical monitors. And then they actually Sloan made a device which actually was hooked up to the first crystal monitor. They would send out a tone, a frequency, and the frequency would change pitch, depending on whether as a quarter wave went through its cycle. So what Inficon did was, with the advent of the microprocessor, they were able to take the frequency of the crystal, and you would program depending on the material that you're evaporating, they had a lookup table. You can program what the density of that material was. If it was 3.0 grams per, square centimeter or cubic centimeter. And so what's happening on the crystal is, as the film is condensing, you're not measuring the thickness, but you're measuring the change of frequency. And so the Inficon microprocessor would take that change of frequency and go through its algorithm on what the lookup table algorithm. You have to tell it, I'm depositing aluminum oxide. And it would then say, oh, you're depositing aluminum oxide. The frequency is changing by X amount. Therefore, it must be this thickness. And because they're calibrated size crystals. And so there's a certain surface area. And so that would give you actually through the microprocessor, tell you what the thickness is from the algorithm that translated the crystal change frequency. Now, with the coating systems, there's one crystal in the center here. Because the parts are rotating and the crystal is stationary, you're not going to get the exact same thickness on the crystal as you get on the parts. So what we do to qualify a chamber is we'll run a coating with 100% equal what we call tooling factor. Then we'll take the witness sample and measure it on a spectrometer, reverse engineer through the TFCalc, what the thickness was, and then add that tooling factor correction into the Inficon. And then that's constant with that process. And that's how we use it.
So does that mean the sensors do you have to clean them, or are they disposable?
Disposable. Okay. Yeah. I'll have to check with my CFO how much we pay, but I think it's like $2.30 per crystal.
Oh, okay.
And we buy them by the thousands. Every run, you throw the crystal away and you put another one in. Yeah, so you're always starting at about 6 megahertz. And that's part of the technician has to always make sure that the frequency is always the same when they start.
I have a question for the gold coating. Excuse me.
Yes.
The gold coating, you mentioned either the enhanced gold coating or enhanced silver coating. Does this coating can pass abrasive test?
No. What the bare gold will not pass an eraser test. It's like trying to clean the top of a stick of butter. And what we would protect it with, it only will allow you to do very mild, say, soap and water rinse with a very soft cotton if you happen to get a fingerprint on it. But it will not pass any sort of abrasion test at all.
But if there's some protection layer that can pass the abrasive test?
Well, the protected layer will, but the gold underneath is still soft. So
okay.
So it's very, it's again, taking my stick of butter analogy, if you were to just take aluminum foil and put it over a stick of butter, it's still going to be soft. You're still going to be able to mark that. People that want hard gold coatings usually have to resort to plating the part, which is a different process altogether. And that might work depending on the application. But for high performance instruments that are looking for, very broadband, 98%, you have to use physical vapor deposition.
Okay, thank you.
You're welcome.
Do we have any other questions? If not, thank Frank again. And
all right, thank you. Thank you.
Quick question.
Yeah.
Physically, what's the size of that?
Oh, well, that's 48 inches. Okay. Okay. So let's see. Yeah. So that's about here.